Hey everyone, we are getting into chapter 14 now, right? Switching from talking about derivatives to integrals. Ooh. So, to start off with, one of the key things that we have to think about when we do integrals that involve functions with more than one variable is remembering the old adage that your Cal 1 teacher hopefully told you, which was that whatever this differential is, that tells you what the values for the bounds are in the integral, right? So if you look at this example, we have dy as the differential, which means that 1 and x are values of y. Now, the thing about functions of several variables is that oftentimes the integrals that we do are going to have bounds that involve variables like this one. So we have to be pretty confident in our ability to evaluate things like this. So remember the way definite integrals work, right? You take your antiderivative and then you plug the bounds in at the end. So how do I do that with something that has two variables in it? Well, I basically use the same trick that I did when we learned about partial derivatives, right? Whatever the variable is in that differential, right? So dy tells me that y is going to act as the variable and any other variable is going to be constant. So when I take the antiderivative of the first term, it's basically just a number times y, not any different than if I did, say, 7y, right? And we know that if I took that antiderivative, it would be 7y squared over 2. So this will be that number, y squared over 2. And of course, the 2's divide, and we can go to the next one. So power rule for our integral here, 3y to the third divided by 3. Remember, you're adding 1 to the power, dividing by the new power. We don't need a plus c for this one because this is definite. Just remember, and this is why I always write the variable next to my evaluate bar. Just remember y is your variable, so 1 and x are what you're substituting in place of y. So with this one, I would get x times x squared plus, and then these 3's will divide, x cubed. That's what I get from plugging the top bound in. Now, if I plug the bottom bound in, remember we're substituting the 1 for y, we can still have an x in our answer. So we have 2x times 1 squared plus 1 cubed. So with that said, I know that this is going to simplify to 2x cubed. Right? We get an x cubed here, like terms 2x cubed. Then I have to distribute the negative, so I get minus 2x minus 1. And that is the antiderivative. So that's still kind of a basic, this is what you would do with one integral type of thing. When we deal with functions that have multiple integrals, a lot of times, or multiple integrals, getting mad at myself, multiple variables, right? A lot of times we want to take integrals with respect to more than one variable. And there are a lot of applications for that, including the actual definition of an integral when we look into two variable functions. So for this one, let's say I have my double integral symbol that the printer just for some reason did not like, right? So first off, this notation is called an iterated integral in your textbook. I look at this and I call it a double integral because you're integrating with respect to two variables. And when we get into this territory, another adage that your Cal 1 teacher hopefully told you was that if my differential tells me that y is the variable, then y cannot be involved in any of my bounds. Right, similarly, if dx is my integral, then x cannot be involved in the bounds for that piece of it, right? Here, the dx goes with the 1 to 2. The dy goes with the 1 to x. So this is fine, right? But keep in mind, if you have variables that are part of your bounds, you have to make sure that the differential is not using that same variable. And this is actually going to make things later on in the video make a lot more sense and be a lot easier for you to track. So the way that this works is basically you have an integral on the inside and an integral on the outside. So you start with the inside, and then after you take the integral on the inside, you do the outside. So here's what it looks like. So I'm not going to mess with the 1 to 2, okay? I'm basically going to evaluate this integral, right? The integral from 1 to x of 2xy plus 3y squared dy. And when I do that, I end up getting, well, this because it's the same function. And now the result of that inside integral is now the integrand for the outside one. So to find the answer to this question, I need to take the antiderivative with respect to x of this thing. So when I do that, we get 2x to the 4 over 4. 2 over 4 simplifies to 1/2. Then I get minus x squared, right? 2x squared over 2, 2's reduce, and minus x. And then we're going to evaluate that from x equals 1 to x equals 2. Right? And even if this wasn't a habit that you had before of writing the variable, I highly recommend that you pick it up. It makes it a lot easier for you to keep track of what variable you're using at what point. So now that we've got our antiderivative, I'll plug in the top number. Then I will plug in the bottom number. Okay, and then I'll just do a little simplifying. So 2 to the 4 divided by 2 would be the same as 2 to the 3, right? Logic. And we know 2 to the 3 is 8. 2 squared is 4 minus another 2. Here I know that 1 to a power, 1 to a finite power, I should say, is 1. So this whole expression will just be 1/2 minus 1 minus 1. Now if I combine like terms, this turns into positive 2. 8 minus 4 minus 2. And this turns into 1/2 minus 4/2, which gives me negative 3/2. But since I'm subtracting, it'll be plus 3/2. If I add those together, I get 7/2. And that is the value of that double integral. Okay, so now that we've kind of seen how double integrals work, one of the biggest applications of it is something that you already know how to do, finding areas bounded by curves. And one thing I will say is that this, I feel, is a lot more intuitive than the stuff that you were taught in Cal 1, Cal 2. So the notation, I'm just going to scratch that out. All right, we have our double integral symbol. I'm going to put R there, and I'm going to put dA there. So the first example we're going to see is finding the area of a rectangular region. And we know what that is. It's just the base times the height, right? But this is to illustrate how we can use double integrals to do that, right? Essentially, this notation tells me the region that I'm integrating over, which I can translate into bounds by looking at the description. dA is a shorthand for me to write dx dy or dy dx. It doesn't assume any order, which is why it's a good shorthand, right? But this is generally a notation that you can use to find area of a region using a double integral. So if we read about R, R is bound by these two vertical lines and these two horizontal lines. So I know that my X values are going from A to B and my Y values are going from C to D. So the way that I would evaluate, the way that I would find the area is to find the integral, double integral over the region R. And then with respect to A, so let's set up our bounds, let's set up our differentials. So with this one, very important that you remember what I said earlier. The differential tells you what the bounds are values of. So for example, if I write dx first, then the inner one has to have x values as the bounds. If I write dy first, then the inner bound has to have y values as the bounds. It doesn't actually matter which order I do it in, I'll get the same thing, kind of similar to how our second partial derivatives worked. So for fun, let's say that I do dy dx for my dA. Okay, so my y's, the bounds are c to d. So the inner integral will have bounds c to d. And then dx is the outer. So the outer integral sign will have the boundaries for x, right? So x goes from a to b. Okay, now if I evaluate this in the way that I showed you in the last example, remember you start from the inside. So I want to take the integral of 1 dy, right? Not doing anything with the outer integral yet. Integral of 1 dy is just y. And we're going to evaluate that from y equals c to y equals d. Okay, and the outer integral is still intact. So when I plug these numbers in, remember you'll need parentheses because there's going to be more than one term. Okay, this is where we are. And I know d minus c is just a number. So the antiderivative with respect to x of a number is just that number times x. And we're going to evaluate that from x equals a to x equals b. So we end up with d minus c times b. That's what I get from plugging the top number in, minus d minus c times a. That's what I get from plugging the bottom number in. And I notice both of these terms have a factor of d minus c. So I could factor out d minus c, and that leaves behind d minus a, which is exactly what we would expect the area of a rectangle to look like. Right? The width times the height, or the base times the height. So let's do a problem that is slightly more interesting. So we want to use an iterated integral to find the area of the region bounded by two trig functions, specifically between these values of x. So here's the thing, we are going to set up a double integral to do this. Yes, you do know how to do this from Cal 1 or Cal 2 whenever you learned areas. Yes, you will end up getting the exact same thing if you do this right. But honestly, I feel like this is a lot more intuitive. So let's think about it. The functions that we were given are all in terms of x, right? And just like with the Cal 1 approach to this, right, we would need to figure out which of these is on top and which of these is on bottom. So easy way to do that is to pick a number that's between pi over 4 and 5 pi over 4. And then take a look at what each value is. So if I pick something easy, I know that pi is somewhere between there, right? So f of pi is going to be sine of pi. We know sine of pi is 0. G of pi is cosine of pi. We know that that is -1. And because there are no other intersections between these two, which you could figure out by setting them equal and solving, right? And you would find that they only would intersect at pi over 4 and 5 pi over 4, right? Because remember, 3 pi over 4, they'll be opposite signs. Right, so since there are no other intersections between these values, we know that for this entire region, right, f is on top and G is on bottom. So we can make a note, top, bottom. Okay. Now that's important for us because when we go to set up our double integral, the area is going to be, just to reiterate this notation here, right? The area for this region is going to be the integral from, we're going to start with dy. The reason for that is because we were given y in terms of x, right? And by the end of this, I want to have a number for an answer, not stuff involving x. So I don't want these to be on the outside. I actually want them to be on the inside integral. So I'll put the bottom on the bottom, cosine x, and the top on top, sine x, right? And because these have x, remember dx cannot be your differential, right? So if it has x in it, then dy should be the differential. Now we are given values of x. We know that x goes from pi over 4 to 5 pi over 4. And that's going to be our outside integral so that at the end of the problem, we're just plugging in a number minus a number. So just like before, we start by evaluating the inner integral. We know that this is going to end up being y evaluated from this to this, right? So rather than writing that step out, I'm going to save myself some space. And I'm just going to write this as top minus the bottom. Oh, gee, look, it's exactly what you would have written out if you were a Cal 1 student. All right. And with that said, we can still do the same thing, take our antiderivatives. So think about it, antiderivative of sine x is negative cosine x. Remember, because we're doing an antiderivative, the things with the positives and negatives are opposite. So with derivatives, derivative of a co is negative. But with antiderivatives, it's the opposite. So with that said, I know the derivative of cosine x, or antiderivative of cosine x would be sine x with no sign change. And then we're going to evaluate that from x equals pi over 4 to 5 pi over 4. And I know if I plug the top number in, cosine of 5 pi over 4 is negative square root 2 over 2. Since there's already a minus here, that's going to give us positive square root 2 over 2. And then with sine of 5 pi over 4, we know that's also negative root 2 over 2. So again, that negative will become a plus. And then pi over 4, we get negative root 2 over 2 minus root 2 over 2. So this will become 2 root 2 over 2, also known as just the square root of 2, minus negative square root of 2, which gives us 2 times the square root of 2. And that's our answer. Okay, now for the next one, we're actually given our setup for the iterated integral or double integral. But rather than evaluating this, we just want to sketch the region whose area is represented by this integral. So first thing I notice is that the inside integral is dx, and we have our bounds in terms of y. So these are going to give us the two graphs that r is between, right? That's going to namely be x equals y squared and x equals 4. So x equals y squared, and I know that's x equals because this is dx, right? Is a sideways parabola that opens up to the right, and x equals 4 is a vertical line. So we know that the two graphs that enclose the region R are going to look like this. It's not going to be the whole region though, right? Because if you look at the next one, dy, remember these bounds give us the values of y. Y only ranges from 0 to 2, not from negative 2 to 2. So because y only ranges from 0 to 2, we're only going to use the top half of that region. So what I just shaded in, that is the region R, right? That is the region whose area we are finding by evaluating that double integral. Okay, now for a slightly tricky one. Let's say we want to find the area of the region R that lies below the parabola given above the x-axis and above the line y equals negative 3x plus 6. The reason that this one is tricky is because you actually have to split this into a couple of different terms. Because if you were to graph this region out, first off, yes, you can. You can factor an x out here. And what this tells me is that you have a parabola that opens down and has x-intercepts at 0 and at 4. So if I were to draw that, 0, that's an x-intercept, and 4, that's an x-intercept. I know that the vertex is going to be halfway between these 2 points. So that's going to be when x is 2. And when x is 2, I can plug that into this equation, and that'll give me the y. So it'll be 8 minus 4, so 4. I have to draw up to 6 for the next one. So 2, 4 is the vertex of this parabola. And I draw that out. There we go. Okay. Now, the other part to this is y equals negative 3x plus 6. So that's a line that has a y-intercept at positive 6 and has a slope of negative 3. So I'll go down 3 over 1. That's going to give me a point of intersection, which I also could get algebraically. Then I go down 3 more over 1 more. That gives me the intercept, which is also going to be important. So then when I draw this out, this is what I get. And keep in mind what the wording said. R is the region that is between the parabola and the line, but always above the x-axis. So R, if I were to shade that, would be that region. All right, which means that we are going to have to split this into 2 pieces, because if x is between negative, or if x is between 1 and 2, then our top is going to be the parabola, our bottom is going to be the line. But if x is between 2 and 4, then the top will be the parabola, but the bottom will not be the line, it'll be the x-axis, 0. So with that said, we have our functions in terms of x. That means that to find our area, the inside integral has to be a dy integral so that our bounds can be these 2 functions. So remember, first thing we're going to look at is between the parabola and y equals negative 3x plus 6. So this is on the bottom, negative 3x plus 6. And on the top, we have 4x minus x squared. Keep in mind, though, this only works for values of x that are between positive 1, that's that point of intersection, and positive 2, that's the y-intercept for the line. So the bounds for our dx integral are going to be from 1 to 2. Now, if I want to get the rest of the region, I have to write a second double integral. Now, the inside is going to be exactly the same, right? Our bounds will be, actually, no, it's not exactly the same. It's the whole reason. All right, so the bottom here is going to be 0, because remember, there we want the bottom to be the x-axis. The top is going to be our parabola, 4x minus x squared. And then the values of, and again, dy has to be the inner one, because if that's a bound, then x cannot be your differential. Then our values of x for that piece range from 2 to 4. So those will be the bounds on my outside integral. So now that I've got that set up, these are the iterated integrals that I would need to evaluate to find this area. So again, start by evaluating the inside. I know that the antiderivative of 1 dy is just y, and I would need to plug top in minus bottom. So I know that when I evaluate the inside integral, I'm going to get this parabola minus negative 3x plus 6. Parentheses are important there because there's more than one term. We have to remember to distribute that negative. And that's what we get from evaluating the inside. Now for the second piece of it, so integral from 2 to 4, the inside integral will end up just giving us the parabola, because subtracting 0 doesn't do anything. So going to the next one, we can simplify this a little bit before we take the antiderivative. So combining like terms, I'll get negative x squared plus 7x, minus the minus gives me plus minus 6. All right. And then for the other piece, there we go. Okay. So now if I evaluate my antiderivatives, for the first part, we'll get negative x cubed over 3 plus 7x squared over 2 minus 6x. We're evaluating from x equals 1 to 2. For the other part, we get 4x squared over 2, also known as just 2x squared, minus x to the third over 3, and we're going to evaluate that from x equals 2 to x equals 4. Okay, I'm going to do some mental math real quick. So that's going to be negative 8/3 plus 14 minus 12. All right. So negative 8/3 plus 6/3 gives me negative 2/3 minus, hold on a sec. Okay, so when you do all that arithmetic, you end up with 15 halves. Okay. So moving on to the next thing. Yep. We're going to actually start looking into volumes. Okay, so with volumes, there really are a couple ways to think about it. You could kind of use the exact same methodology that we did with areas with double integrals and instead do a triple integral, right? But the way that your textbook shows it actually shows you a way to set these kinds of problems up with double integrals. And it's kind of important here because it really gives you a way to see what the true definition of a double integral is. So let's kind of compare that. Back in Cal 1, you learned that the definition of an integral is that it's the limit of Riemann sums. Right, so remember your Riemann sums were where you took the area between two curves. You divide it into rectangles, you find the area of each rectangle, you add them together, and then you take the limit of that sum as the number of rectangles gets larger and larger. Well, there is an equivalent to that for volume and double integrals, right? So a double integral would be defined as essentially finding the volume of basically rectangular prisms, right? So the xy part of it gives you the base of the prism. The z coordinate would give you the height of the prism. You would basically break the space underneath the three-dimensional surface into rectangular prisms the same way that you broke this kind of space into rectangles, right? It's just now instead of a rectangle, you have a whole box, right? In other words, rectangular prism can be scary. Think of it as a box, right? So um, if you were to do that and take the limit of the sum of those volumes as the number of rectangular boxes gets larger and larger, that's the definition of a double integral. So let's take a look at this first one. We want to approximate the volume of the solid between this paraboloid and a square region where x is between 0 and 1 and y is between 0 and 1. We want to use a partition made up of squares whose sides have a length of 1/2. And when you see this partition, don't get scared by that word. It's really just telling you how to divide up the XY base part of it. So with that said, if I were to use squares whose sides have a length of 1/2, right? I would have a square where x is between 0 and 1/2 and y is between 0 and 1/2. Okay. I would have a square where x goes between 1/2 and 1, and y goes from 1/2 to 1. But think about it, a paraboloid, if you were to draw it out, was basically like this. That was our quick, easy ghost costume for Halloween graph, right? This guy here. So if we had, so if we basically had squares in this region with the partitions that we're saying, x goes from 0 to 1/2, y goes from 0 to 1/2. X goes from 1/2 to 1, y goes from 1/2 to 1. That only actually takes into account part of, or just like half of the prism, right? So I would still need to go back and use, so this is one of our partitions. This is a second partition. I'm also going to have partitions where x goes from 0 to 1/2, but y goes from 1/2 to 1. And likewise, I'll have partitions where x goes from 1/2 to 1 and y goes from 0 to 1/2. Right. That's going to give us those missing two squares there. And where this becomes a box is basically we can evaluate the z coordinate, or at least the bounds of the z coordinate, using the function that we're given here, right? And that's going to give us the height of these boxes. So if I were to take like this little piece here, essentially it's going to be this little square as your base, and then it goes up as high as the z coordinate goes. They see it makes a box, and we have 4 of them. So basically we need to find the volume of each of those 4 boxes. So we know that the area of each of these bases is going to be 1/2 times 1/2, right? So no matter what, these side lengths are all 1/2. And that tells me that the base has an area of 1/4. So I have to multiply that by whatever f of these different things gives me. Right. And just like we had left and right Riemann sums for Raman. just like we had left and right Riemann sums for functions of one variables, we can kind of do something similar with these, right? Because if you look here, these are not coordinates, these are intervals for x and intervals for y. So x can be anywhere between a half and one, y can be anywhere between a half and one. So we can pick something that's one of those endpoints. We could pick something that's in the middle of the endpoint, right? And they'll all give us different answers, and they'll have varying amounts of accuracy, right? So let's say I do the equivalent of a left-hand Riemann sum, where I use the values that are on the left for both variables. Right. So the z coordinate, if I use 0 for both, would be 1. Yep, so that would correspond to this partition. The volume would be equal to 1/4, that's the area of my base, multiplied by 1. That's what I get from plugging the left-hand number for x and y into this function f of x, y. Then for this partition, right, the area of our base is still 1/4, right? X times y, or change in x, change in y, right? And then the height of the box we would get from plugging 1/2 in for x and for y. So if I do that, 1/2 squared gives me a fourth times another half gives me an eighth. So basically I have 1 minus 1/8 minus 1/8, which gives me 6/8, which is the same thing as 3/4. Then for this partition, we would plug 0 in for the x, we'd plug 1/2 in for the y, and this would end up giving me 1/4 for the base still, because that's change in x times change in y. And then for the height, we'd plug 0 in for x, right? And that would get me, and 1/2 in for y, so that would get me 1 minus 1/8, should be 7/8. Then for the last one, I would plug in 1/2 for x and 0 for y. So area of the base, still 1/4. And I would end up also getting 7/8 for that z coordinate. So now that I've got all of those volumes for each partition, I can get my approximation for the overall volume, right? That would be the volume of the space that's underneath the paraboloid, but above the xy plane, by adding these different volumes together. So we get 1/4 times 1, which is a fourth. 1/4 times 3/4, that's 3/16. Then 7/32, and another 7/32. So I get 14 plus 4, or actually, no, that's not true. I have to have the same denominator. So we have 14 from adding these together. Which, if I want to, I could reduce that to 7/16. Now I can add it with that one. 7/16 plus 3/16 gives me 10/16, which does also reduce to 5/8. So if I have 2/8 plus 5/8, I get 7/8. And that would be the approximated volume of that region. And another side note before I move on is that here I used the left side of each interval for x and y. I have options. I could have used the right. I could have used the midpoint. I could have used the left for one and the right for another, right? And they would all have different implications on the accuracy and whether I over or underestimate, but there's no AP test, so I'm not really going to talk much about that one. All right, so that said, let's look at an example where we calculate exact volumes. So this double integral that we have here, and I really wish this would stop screwing my notation up, right? So this double integral that I've written out here is a way for us to get the exact value of what it was that we just estimated. And I'm going to start by saying what we did was kind of a crude estimation because I used really big step sizes because honestly, I didn't want to find 16 volumes like the textbook did. So I made my step sizes 1/2 instead of 1/4. But yeah. So we're probably not going to be super accurate. But this is how you get the exact thing, right? Take your double integral. So here we are given that R is a square region, X is between 0 and 1, Y is between 0 and 1, right? Just like in the last problem. So I know that I can set my bounds up so that my X's and Y's both go from 0 to 1. Because that is the case, right? Both are 0 to 1. It doesn't actually matter if I do dx dy or if I do dy dx. In fact, if you would like to get more practice just doing these integrals, I invite you to pause at the end of the example and try it with the other order. All right, but anyway, okay. So I'm going to do dx dy. Okay. So remember, you start from the inside. My inside integral is a dx integral, so any y's that I see are going to be treated like constants, and any x's I see, I have to use my regular typical rules of integration. So taking the antiderivative with respect to x, 1 will become x squared over 2 will become x to the third over 2 times 3, so 6. And then y squared over 2 is just a number because we're anti-differentiating with respect to x. So this is a number, which means that the antiderivative will just be x times the number. And we're evaluating this from x equals 0 to x equals 1. And remember, these are only being plugged in for the x. Again, it's very helpful if you take up this habit of writing what the variable is when you do your bar thing. So 0, or so I have 1, plugging in the first number, 1 minus 1/6 minus 1 times y squared over 2 minus, and then I plug 0 in, everything here would be 0. And integrate dy now. So combining these, this is going to become 5/6. So we have 5/6 minus y squared over 2. If I take the antiderivative with respect to y, that will become 5/6 y. Y squared over 2 will become y cubed over 2 times 3, also known as 6. We're going to evaluate from y equals 0 to y equals 1. So when y is 1, we get 5/6 minus 1/6. And when y is 0, we get 0. So altogether, that's 4 over 6, also known as 2/3. All right. Now, next to the last example, I'm going to preface this by saying that this example involves a nasty Cal 2 integral. It actually involves a trig sub. Because I don't want to spend time on the video reviewing trig sub, I'm going to get to the integral and then I'm going to give you the answer. But I will post a document where I write out step by step how I did the integral. Because it is important for you to remember the old stuff, even if I'm not evil enough to make that a test question. All right, so here we go. Find the volume of the solid region bounded by a paraboloid and the xy plane. And then I just said what I told you in words. All right, so all right. So basically we want to find the antiderivative of this, right? From z equals 0 all the way to the top. Now to get us started on it, right? Think back to Cal 1, when you had to do questions where you were finding area between curves. One thing that you had to do was figure out the intersection points, because typically that would be the bounds that you're using. So for this one, we know that for the xy plane, the z coordinate is equal to 0. For every other point on the surface, z is equal to whatever this is when you plug in the x and y. So I can find my intersection points by setting those two things equal to each other. Okay. So basically, all right, so basically I want to figure out what the curve of intersection is between that paraboloid and that plane. All right. Judging by this, I know that I should move the x squared and the y squared terms to the other side. So I'll do that. Judging by this, it looks like it's going to be a conic section. So I want to divide everything by 4 to make this into standard form. So I get x squared over 4. Actually, that's not how I should do this. Yeah. Yeah, no, backtrack, this is a horrible eraser. Backtrack. All right, so reason I'm backtracking here. What I was showing you would be a way that we could do this if we were doing the volume with the triple integral. However, to show you what you're gonna basically be expected to do in your homework, I'm gonna change gears and I'm actually gonna show this as a double integral, which is still gonna involve the nasty trig subintegral thing that I mentioned. But to do this, I'm going to need to solve for one of the variables. It doesn't really matter which one I do. So I will solve for x. So I get x squared is equal to 4 minus 2y squared, which means that if I square root both sides, x is going to be equal to plus or minus the square root of 4 minus 2y squared. So now that I know my x in terms of y, I know that when I go to set up my volume, my inside integral is going to be a dx, and my bounds are going to be from negative square root of 4 minus 2y squared to positive square root of 4 minus 2y squared. Because this is a volume problem, and this is the difference between a volume and an area problem. With area problems, our integrand was always just 1. Right? But with volume problems, when we address them with double integrals, we use the function for the three-dimensional surface as the integrand. Okay, and because these involve y, we know the first differential has to be a dx. Okay, and now we need to figure out what the values of y are going to be for this. Okay. All right. So at this point, I know that the z coordinate goes from, yep, from 0 to 4, right? So if the z coordinate goes from 0 to 4, let's think about what the maximum possible value for x or y could be. All right, so one way to figure out the max would be to zero out one of the integrals or one of the variables. So if x were equal to 0, in order for y to be equal to, for z to be equal to 0, right, we would have z equals 4 minus 2y squared, right? So let's write that out. 4 minus 2y squared equals 0. So if I were to solve for this, I would get 4 equals 2y squared, divide both sides by 2, And I would end up getting that y is equal to plus or minus the square root of 2. Now, another thing to consider here is what if the y were being zeroed out? I know that for my z to be 0, x would have to go from negative square root of 2, or negative 2 to 2. Right, both would end up giving us a value of 0. All right. The other thing to consider with this one is what the maximum value of z would be. Right. So our maximum value of z would be z equals 4, which will only happen if x and y are both 0. So I have these bounds potentially for y, and yeah. And then I have this other one to consider, y equals 0, right? So one thing that I could do going from, cat keeps meowing. So one thing that I could do is I could go from negative 2 to, or negative root 2 to 0, 0 to root 2, right? That would be kind of silly though. So I'm just going to go from negative square root of 2 to the square root of 2. Okay. And again, we would get this by zeroing one of the variables and trying to figure out what makes our maximum and minimum z values. Right. So I mentioned I would get to the integral and I would tell you the answer, and that would be that. So the answer ends up being pi over 32. All right, so like I said, it ends up being a nasty trig subintegral that we should be able to do with maybe some review, but yeah, not going to spend time on that. All right, so now the last application that I'm going to talk about in this video is finding average values. So remember when you were in Cal 1 or 2, I don't know when this is, I don't remember when this is taught. You learn how to find average value by basically just doing the integral from a to b of the function whose average you want divided by b minus a. When we have functions of several variables, remember how double integrals are defined. They're not defined by rectangles that have a width, right? They're defined by boxes that have a rectangular or a square base, right? So rather than dividing by b minus a, we actually divide by the product of our, basically the area of our base, right? So if we look at this example, we have the average value of this function over a plane region R. R is a rectangle. Okay. So we know that A, so if I were to draw out these vertices, essentially I would get a rectangle that has dimensions of 4 by 3, right? And the area of that would be equal to 12. So I know that this A is going to be 12. The z bar is going to equal 1 over 12 multiplied by our double integral. So again, it doesn't matter what order you do the x's and y's in as long as you're consistent in your notation, right? So I know that from looking at these vertices, my x's range anywhere from 0 to 4, and my y's range anywhere from 0 to 3. Since these 0 to 3 are y's, dy will be my inner and dx will be my outer, right? You could have also set this up the other way and you'd still get the same answer. And I forgot something because I'm silly, right? We're actually supposed to put the function in there. Yep, there we go. All right, so taking my inner integral, got the integral from 0 to 4, right? With respect to y, remember x is a constant, so this will be 1/2 x is a number times y squared over 2. So we get x y squared over 2 times 2, 4. And we want to evaluate that from y equals 0 to y equals 3. Okay, so when I evaluate at these endpoints, remember these are plugged in for y, right? So we get x times 3 squared over 4 minus x times 0 squared over 4, which will just give me 9x over 4. Okay. So then when I take the antiderivative of this, I end up getting 9x squared over 8. So I have my 1/12, 9x squared over 8, and we're evaluating that from x equals 0 to x equals 4. Number sense trick here, 4 squared is 16. I know that 16 divided by 8 is 2, so I don't need to go through the trouble of times 9 divided by 8, right? I could do this pretty quickly by just remembering that. So 16 divided by 8 is 2, times 9 is 18. If I plug 0 in, I'd get 0. So I get 18 over 12, which reduces to 3 halves. And that is the average value of f of xy over the rectangular region R. So in summary, when you integrate functions that have more than one variable, right, you kind of take a similar approach to partial derivatives, but with integrals. So you can take the antiderivative with respect to one variable while treating the other one like a constant. For this, you do need to be very careful that you know which differential you're dealing with, because the bounds have to correspond to that differential. So if my differential is dy, the bounds are y values, and I cannot have y as either of those bounds. Right, and then other things, just remembering to go inside and work your way out. Other than that, we talked about area, right, which you can take as just the double integral of dx dy or dy dx. You set up your bounds correctly. And volume, where you take the double integral of a function, and likewise, you set up your bounds in a similar manner. So with that said, gonna let y'all off. That is all for the first video of chapter 14. Happy mathing.